Many similarities between the components of the AC generator and those of the electric motor, but with a few differences. The AC generator consists of a coil with many turnings, like that in the motor. It also has a strong magnet with two poles, a north and a south. But unlike the electric motor, in the simple AC generator there is no power supply. We rotate the coil using hands or any other means of rotation. Each end of the two ends of the coil is connected to a slip ring. So we have two separate slip rings that are not in touch with each other. Each slip ring slips on its own carbon brush to conduct the produced induced current to any external circuit. The galvanometer is just to indicate the passage and the production. Also, it shows the direction of the induced current produced. To study the basic concept of how the AC generator works, it will be a good idea to study the electric AC current produced by the AC generator. If we draw a representation of how the produced AC current or AC voltage varies with time, this sine wave is what we get. Now let's find out the characteristics of the produced current according to the graph. Characteristics of the AC current from the AC generator. The first thing that we can observe is that the current has positive and negative values. As a vector quantity, this means that the current produced by the AC generator flows in opposite directions. So we can say that the AC current is reversing. In other words, having positive and negative values. Another obvious thing is that no specific values or strength of the current. It can take any value between a maximum and a minimum. So the second characteristic is that AC current is variable. In other words, can take any value between a maximum and a minimum. The next part will be explaining why the AC current produced by the AC generator is reversing and why it is variable. Clear explanation of the reversing and the variable nature of the AC current produced by the AC generator. We must have a direct look from the front of a working one. And study what are the changes that happen to the side wires of the coil in one complete cycle. The first feature to discuss is why the induced AC current produced by the AC generator is reversing and flows in opposite directions. This is how we look to the AC generator to get a front view. The red circle at the top of the coil is the front view of one of the side wires of the coil. The blue circle at the bottom of the coil is the front view of the other side wire of the coil. The side wires are the only parts of the coil that are responsible for cutting the magnetic field lines and hence generating electricity. The parallel black arrows just appeared represent the imaginary uniform magnetic field lines between the poles of the magnet. Let us first concentrate on the red half of the coil. On rotating the coil by hand, this is what happens in one cycle. Half of the cycle, the side wire represented by the red circle, cuts the magnetic field lines downwards. This produces an induced current in a certain direction. The second half of the cycle, the same side wire cuts the magnetic field lines in an upward direction, and this will produce an induced current in the opposite direction to that current produced in the first half cycle. This can be summarized as: the AC current produced by the AC generator is continuously reversing, because the side wires of the coil reverse the direction of cutting of magnetic field lines each half cycle. The first half cycle the cutting is downwards, and the second half cycle the cutting is upwards. This produces the current in opposite directions. After we answered why the AC current produced by the AC generator is reversing, now it's the time to explain why it is variable. The values of the current change with time. It does not have specific values. Current intensity can be any value between a maximum and a minimum. Before discussing the rules of the side wires of the rotating coil, there is something you need to understand before. 3 examples will study the effect of the angle of cutting on the intensity of the produced current. In the first example, the wire is moved in a direction that cuts the magnetic field lines perpendicularly. This type of motion, which is described as perpendicular cutting, will give the maximum possible current. In the second example, the wire will cut the magnetic field lines with the same speed, but this time with an angle which is less than 90. This cutting with an angle will give a smaller current than previous. In condition, the speed of cutting is the same. This is because the rate of cutting of the magnetic field lines with the wire is less. In the third example, the wire will move parallel to the magnetic field lines. In this case, there will be no cutting at all, and hence no current is produced. A type of motion which is named parallel motion will give zero current. Now let's apply these cases to see what happens to the side wires of the rotating coil during one complete cycle of rotation by hands. Again, we will concentrate on one half of the coil, the red half. As the coil starts to rotate, the side wire, which is represented by the red circle in the front view, will move parallel to the magnetic field. This will give no current according to what we said before about angles of cutting. As the side wire continues rotation, the cutting starts to have an angle with the magnetic flux lines. This will give a small current. As rotation continues, the motion and cutting will have a greater angle, which will give a strong current intensity, but still the angle is less than 90 degrees. In this position of the cycle, the side wire is moving to cut the magnetic field lines in a perpendicular way. This will give the maximum possible current of the cycle. Now the cutting is again having an angle which is smaller than 90 degrees. This will give a smaller current. As the angle of cutting decreases more and more, the current will also decrease, until the coil takes the position where the motion is parallel to the magnetic field lines, and the current again will be zero. The same changes exactly will take place in the second half cycle for the same reasons. This makes the same changes to happen, but with the current in the opposite direction. When the side wire is at the top and the motion is parallel, the generator produces zero current. In the extreme right, the motion is perpendicular to the magnetic field lines, and the current produced by the generator is maximum. When the side wire is at the bottom of the motion and is again parallel to the magnetic flux lines, the generator produces zero current again. In the extreme left, the motion is perpendicular to the magnetic field lines, and the current produced by the generator is maximum but in the opposite direction. The changing current with time during one complete cycle of the coil of the AC generator can be represented as follows. At 0, this will be the direction of the motion parallel to the magnetic field lines. As current increases, this means that the cutting is having an angle. At the peak of the curve, this means maximum current, and this indicates the shown position of the coil cutting perpendicular to magnetic field lines. As current decreases, this means the cutting now take an angle which is less than 90. The zero current means parallel motion to magnetic field lines. The current is now increasing, but in the negative region, because the angle of cutting increases, but in the opposite direction. This means that the current increases, but in a direction opposite to the first half of the cycle. The trough of the graph indicates maximum current in opposite direction. This indicates perpendicular cutting but in opposite direction. Again, current decreases as the angle becomes less than 90. And finally to the start position where current is zero due to parallel motion. Taking a 3D look may improve your understanding. To increase the intensity of the current produced, we can increase the number of turnings of the coil. We can use a stronger magnet to increase the strength of the magnetic field and the number of magnetic field lines. We can use an iron core. This will concentrate the magnetic field lines near the coil. Finally, we can rotate faster. But rotating faster will increase the current and the frequency of reversing of the current as well. And now a summary of part 1 of the electromagnetic induction, moving the wire. Two main titles: moving a single wire in a magnetic field and the AC generator. Under moving a single wire in a magnetic field, we had a simple experiment and explanation. We learned how to get the direction of the induced current by Fleming's right-hand rule and methods to get stronger current. Number 2, the AC generator. We studied the parts of the AC generator. After that, the relationship between the AC generator and the produced AC current. We answered two questions: why is this current reversing and why is it variable? After that, we drew the graph of the AC current produced from the AC generator, and after that we learned how to get a stronger current.